So is it ever going to happen? Like, are we gonna get nuclear plants of
The outlook is mm, that depends how much you're willing to stretch the definition of possible.
I'm glad that I'm not going to be shot with a plasma gun anytime soon. That's nice to know. Hello, and welcome back to another season of Physics Chat. Yes, we are on season 5, and we are not done chatting. I'm here with my wonderful co-hosts, Tian and Sergi. I'm Sophie Newman, and I'm a first-year PhD student studying galaxies at the Institute of Cosmology and Gravitation. I recently joined the team, and I'm really looking forward to all the amazing discussions we're going to be having in season 5. On today's show, we have the amazing Imogen Gingell, who's a space plasma physicist at the University of Southampton. How are you doing today?
I'm very good, thank you. Thanks for having me on the show.
Imogen, we'd like to get to know you a little bit. So can you tell us what kind of things you like to do in your free time?
Well, I guess one thing that I'm really kind of embedded in terms of what I do with my free time is I'm a huge fan of like tabletop role-playing games. I don't know if you played Dungeons and Dragons and so on. So I spend a fair amount of my free time doing freelance writing for Dungeons and Dragons and Stormlight RPG and all these kinds of things. So I put down my academic papers, I pick up a different document to start writing in. So I just do a ton of writing. It's my life.
So to get started, Imogen, could you try to summarize your research for us in one sentence, please?
Okay, one sentence, always a challenge. I am researching how solar wind plasma, that's plasma ejected from the sun, interacts with Earth's magnetic field and all the kind of fun physics that goes on when that plasma is deflected and absorbed by Earth's magnetic field and atmosphere.
That sounds very interesting. I've heard of plasma before, but I'm not really sure what it actually is. Can you tell us what it is and how do we study it?
So plasma is sometimes called the fourth fundamental state of matter alongside solid, liquid, gas, and plasma. It makes up about 99% of all ordinary matter in the universe. So pretty much everything is plasma. We're the unusual ones here down on a rocky planet. But plasma is a fluid where the atoms have become dissociated so that their electrons split away from the constituent nuclei. Rather than having, say, a gas of hydrogen with, hydrogen nuclei and electrons going around, the electrons jump off and can move around separately in their own fluid. So because you have those separated charges, the nuclei, the ions, the hydrogen, the helium, and so on, from their electrons, they can interact very strongly with electromagnetic fields. And that leads to a whole bunch of new and kind of interesting physics, which is the kind of stuff that we're interested in this group.
Right. So that's very helpful. So what made you first interested in studying this?
So I kind of came into this field by a relatively traditional route. I kind of discovered a love of the plasma physics side of space and astrophysics just via doing the undergrad course. So I studied natural sciences at Cambridge with astrophysics. And I found myself just really enjoying that side of astrophysics because the plasma physics involved in all that is something you can very much see with your eyes and you can go there. So you can see the sun, you can see all these wonderful arcs and prominences on the sun's surface. And it only takes a small solar telescope to do that. The plasma physics associated with the solar winds, that is the kind of plasma moving through interplanetary space, you can put a spacecraft in there and measure it. You know exactly what it's like to be in these places, as opposed to some of the more traditional astronomy where you're relying on looking at very distant objects and trying to draw inferences from them. So it felt like a very kind of hands-on approach to astrophysics, which really kind of drew me in. And then when I did my PhD, I actually ended up doing a plasma physics PhD in nuclear fusion, where plasma physics is critical to how certain fusion power plants would work. And I haven't looked back.
That sounds like a very interesting path. Yeah. Uh, Maybe a bit related to plasma. Now you can tell us. Recently, in lots of parts of the UK, we were able to see the Northern Lights, even in Portsmouth. I don't know if you saw them.
We did see them in Southampton, yes.
Nice. So, can you tell us about the physics behind that? Is it
Of
related
course.
to the things that you study?
Yeah, yeah. The journey towards generation of the Northern Lights kind of starts at the sun. So, as I mentioned, there is a solar wind. Solar wind is this plasma that's emanating from the sun constantly, every direction. And the solar wind is a very variable medium. It's always changing. The magnetic field of the sun is being dragged out through that solar wind. And the sun itself also undergoes some very energetic processes which can launch spectacular eruptions of plasma into the solar wind. So you may have heard of solar flares. These are at points where the magnetic field on the sun becomes intensely twisted and pinched, and that releases a blast of X-rays and high energy particles. But we also have something called a coronal mass ejection, and that is where the magnetic field kind of breaks away from the sun's surface, and that sends a whole heap of plasma racing through the interplanetary space at kind of supersonic speeds. So when when the solar wind and when the coronal mass ejection reaches Earth, it interacts with Earth's magnetic field. So we have this principle in plasma physics called the frozen-in condition, which says that plasmas can't mix across magnetic fields. So rather than the Earth acting as an obstacle to the sun's solar wind, it's Earth's magnetic field. And that creates a bubble around the Earth that protects us from the worst of solar radiation. So that's called the magnetosphere. Here's where the complicated part happens. So I'm going to use a little Earth plasticine model that I prepared earlier. So if you imagine the Earth here, it has a magnetic field that's a bit like a bar magnet. So it has loops of magnetic field around it like that. When the coronal mass ejection, when any solar wind impacts upon that magnetic field, it bends and deflects around Earth, forming a bubble kind of like this. And that gets drawn backwards behind Earth and stretches out the magnetic field really far behind into what's called the magnetotail. So when a coronal mass ejection comes along, that's a huge extra load on this system, and it erodes the magnetic field on the day side of Earth in a process that we call magnetic reconnection, where magnetic field lines kind of get broken apart and stitched back together. And when it does that, it releases a whole load of energy. So the solar wind comes in, it reconnects with Earth's magnetic field, loads it all up, and all that magnetic field piles up in the night side of Earth. And then in the stretched out tail of Earth, that magnetic reconnection happens again. And when that happens, all the magnetic field that's kind of bulged up and stored up here snaps back. It releases an enormous burst of high energy particles. Those high energy particles flow along Earth's magnetic field down into the poles and impacts with Earth's atmosphere in a ring around the pole surface. So when those very high energy particles hit the upper atmosphere, they interact with the gases there and cause it to glow. And then you get the kind of nice ring of glowing lights around the poles, the North and the South Pole at the same time, which is the Northern Lights.
That is very
That's
cool.
so cool. Yeah.
So I guess then it makes sense that the reason why you see them in the North Pole or South Pole is because they are following these magnetic field lines which end up there. So if you want to see them, you should be as close to there as possible, no? But if it's big enough, like it was, then we can also see it even far, like more away from the poles.
Exactly, yeah. So during very large during any coronal mass ejection, when you erode that magnetic field. The ring over which you see the aurora, it's called the auroral oval, drifts down to kind of lower and lower latitude. Under typical conditions, maybe a minor geomagnetic storm, you're typically going to be seeing the aurora around roughly the Arctic Circle. So this is why it's common to see it in the northern parts of Norway, Sweden, Finland, Russia, and so on. But when you have a particularly large coronal mass ejection, yeah, that oval drifts downwards. And as we saw back in May, it can push it down all the way down into the UK and even further south during these very extreme conditions. So the one in May was actually one of the strongest solar storms to impact Earth in a very long time. So we had very exceptional and very good conditions. And thankfully, very little cloud cover, at least in Southampton and Portsmouth. So yeah, we could see it all happening here.
Because it's one of the stronger, like one of the most strong solar storms you've seen in a long time. Does that mean that your group maybe got extra data? Like, was it extra good quality, or is that not how it works?
Actually, in some ways, for the particular instrumentation that we have in this group, which is stationed in Svalbard and Norway and Sweden, it's actually somewhat worse because the auroral oval was lower latitude than where all the instrumentation is. So in that sense, it's not necessarily the best viewing conditions for us. On the other hand, in terms of the kind of global efforts of research in this field, it's a fantastic opportunity.
So back in May, on that Friday, when I heard that there's a largest ever solar flare that I can see in my life, I immediately know that we can see it around Portsmouth. And I've seen lots of images from Stonehenge with aurora light. And those images are really great. But this time, it is like the northern light is above Stonehenge and it's on top of my head. It's unlike the usual past images where the northern light is above the horizon. So I just went there and everything was fantastic. And there are lots of people taking pictures of the Stonehenge and the northern light at the same time as well. So it's really amazing back in May.
It's kind of like a life-changing experience to see the northern lights for the first time.
Yeah, Tian is our, I think, local astronomy expert, at least for me. So like, I remember when you came to the office that morning, you like the first thing you said was like, okay, today we're gonna see the aurora. I'm like, what do you mean? Yeah, so it's good to have him in the office to hear the latest astronomical news
and to show us all of his astrophotography, which is insane.
Yeah, the rest of them are physicists. I am astronomer.
So often when we do see the northern lights, like Tian did when he went to Stonehenge, sometimes you can see different colors. Like I saw some green, a bit of red. And when you see like the really good pictures, you can kind of see like little waves, kind of curtain-like-ish. Do they have meaning, or are they just random?
So there's a ton of physics involved in the way the aurora look and the colors that you see. So you tend to see a green at the bottom. So that comes from oxygen in the atmosphere. When you go a little bit higher, you tend to see, particularly under extreme conditions, a kind of red haze above it. That's also from oxygen, from a kind of different oxygen atomic transition. So you get the different colors because the electrons from that high energy particles coming down from the magnetotail, they interact with the neutral atoms in the atmosphere and molecules, and those become excited. And then eventually those atoms kind of de-energize by releasing a photon. And the energies that the photons get released are very precisely determined by the kind of quantum mechanics of those atoms and molecules. So the green oxygen you see is one kind of photon coming off from an oxygen, and the red is from another one. You can also see sometimes a kind of blue-green or purple that comes from nitrogen. The reason you see kind of a gradation of the color rather than just a mix of colors everywhere is just because these different species have different abundances in different layers of the atmosphere. In terms of the actual structuring that you see in it, that's all very strongly determined by Earth's magnetic field, which means that when you see the kind of bands, the vertical kind of diagonal stripes in the Aurora, you're seeing plasma stretched along Earth's magnetic field.
That's very cool. Thanks for explaining that. Yeah, the Aurora is very beautiful, all the patterns and colors, but I think it's even better when you can understand some
Yeah.
of the physics and the chemistry behind these things. It definitely makes it better. So you mentioned before that some of the instrumentation of your group is somewhere in the north. Have you ever gone there, or like, can you explain what is there?
So unfortunately, I've never actually been in person to our instrument sites.
Maybe in the future.
Which maybe one day, yes.
Yeah.
But we do have a couple of instruments on Svalbard itself. So it's an extremely remote island in the Arctic Circle. Maybe one day I'll go and I'll get to see the Northern Lights up there one day. But my research is mostly to do with the plasma physics that happens a little further away, run on the supercomputer we have here in Southampton.
Yeah, it would be cool to visit the spacecrafts as well.
Yeah.
That would be
maybe a bit more of a sci-fi wish there. Yeah.
Talking about sci-fi, here's a big road question. In a lot of science fiction movie, we see things called plasma guns. So that something looks like a laser but explodes. So is that things physically possible?
That depends how much you're willing to stretch the definition of possible. Like plasma guns as you see them in sci-fi don't really exist, at least not in any kind of meaningful way that you could call them a weapon. That said, some of those, depending on how hard sci-fi you're getting, are kind of based on some real things. Because plasmas are highly dependent on magnetic fields and electric fields, you can use electromagnetic fields to control what they do to a certain extent. Some people have done research into kind of exploiting that same property of tying plasma to magnetic fields and electric fields to make projectiles in a way. Like you can have a system where you have two kind of charged rails. So you may have heard of a rail gun where you have a ball and two charged rails, and you can accelerate the ball and then shoot it. And that you can build a reasonable weapon out of that. So there are ideas about using a same system where instead of like a metallic ball, you use a glob of plasma, and you can accelerate the plasma along those electrodes. But the systems in which that work only really work in a vacuum, and they don't really produce anything dangerous. You can kind of use it for spacecraft thrust in a way, but you're not going to be damaging anything with it, at least not current technology. So it's still very much the realm of science fiction, but it's not entirely, it's based on some real stuff.
I'm glad that I'm not going to be shot with a plasma gun anytime soon. That's nice to know. So it's time for the most important part of the show, which is the random question. Although I would say that question was also pretty random, but how long would you stay in an igloo?
Is that I like to think of myself as somewhat adventurous. I reckon I could make a couple of nights in an igloo. I think it'd be fun to try. I think eventually the cold would probably get to me and I want to come home. But, I'd tough it out for a couple of days just for the experience. And I guess if we are, in the North or South Pole to stop our igloo from melting, then, maybe I'd stay longer if it's during some high solar activity we get to see the aurora.
I'd like to ask you one more question because it's not very common to find someone who has studied a lot nuclear fusion. There's always this thing, right? That nuclear fusion is always like 10 years from the present, and it's been like this for maybe, I don't know, 50 years. You can tell me. So is it ever going to happen? Like, are we gonna get nuclear plants of fusion that can be efficient?
It's tough to say. So this is speaking as someone who's now been out of that particular field for a little over 10 years, but the outlook is there are a lot of engineering challenges that still need to be solved. I think because those challenges require very expensive systems to, do a good experiment with, it does kind of slow down the the research process a bit because you have to start bringing in international politics and budgetary requirements into your science, which always is going to slow things down a lot. And that's been one of the kind of major hurdles to really getting it over a finish line. So I'm sorry to say it's probably still a good 40 years off, as it always is.
No, that sounds more realistic, I guess. No, 10 and then 10 and then 10, yeah.
We'll see. It's an exciting area of physics and engineering. So fingers crossed it goes somewhere. Yeah, but it's still a while to wait. Yeah.
Well, Imogen, it's been so interesting hearing about your research, both your past research and your current research. Learning about how plasma from the sun interacts with Earth's magnetic field, which is just, for me, it's crazy to think about, but it's so cool. Yeah, we'd love to hear from all of you watching. We want to hear how long you think you would stay in an igloo. But for now, from everyone here at Field of View, we hope you have a really great day and goodbye.
Bye.
Bye.
It's kind of like a life-changing experience to see the Northern Lights for the first time.